mn greater than 2, n minus 1 factorial minus n times n minus 2 factorial equals m times m minus 2. Did I write that correctly? Okay, so my first instinct is to factor some stuff. The n minus 1 factorial minus n makes things a bit difficult because it doesn't actually have a factor of n in it. So here's what I'm going to do instead. I'm going to distribute minus n times n minus 2 factorial equals m times m minus 2. Okay, and now, yeah, so basically what we want to figure out is we want to put the left side in the form of the right side. So what I'm going to do is factor out n minus 2, and so we get n minus 1 factorial times n minus 3 factorial minus n times n minus 3 factorial. And there is your form. So, oh, not quite, because m is the same. So we need the same thing over here as what's in here. Okay, how about this? I'm gonna try leaving it as n minus 2 factorial. And what if we set m equal to n minus 2 factorial? Then we get n minus 2 factorial times n minus 2 factorial minus 2. That doesn't quite work, does it? Alright, then let's try this. 1 times 2 times 3 times n minus 1 minus n. 1 times 2 times 3 times n minus 2 equals m times m minus 2. Alright, let's set k equal to n minus 2 factorial. Then we have n minus 1 factorial minus n times n minus 2 factorial equals k times n minus 1 minus n times k. Alright, and that equals k squared n minus 1 minus nk, which equals nk squared minus nk minus k squared. So let's group the n's together. Actually, yeah. And we can rewrite this as nk times k minus 1 minus k squared, which equals k times n times k minus 1 minus k. Not sure if that actually helps. Yeah, this substitution k equals n minus 2 factorial seems helpful because it simplifies the equation a bit. But I'm not quite sure where to go from there. I suppose we could solve for m, and if we... Actually, this might work. If we add 1 to both sides, k squared n minus 1 minus nk plus 1 equals m squared minus 2m plus 1. We have m minus 1 squared, and so m minus 1... Oh, wait, hold on. So the square root of k squared n minus 1 minus nk plus 1 equals m minus 1. So we have m equals square root of n minus 2 factorial squared times n minus 1 minus n times n minus 2 factorial plus 1, and then plus 1. So I guess the question is, when is this the inside of the square root a perfect square? And we have to treat it like a quadratic. in terms of k. N minus 1 k squared minus nk plus 1. So when is this a perfect square? Well, first we can factor out an n minus 1. And we get k squared minus n over n minus 1k plus 1 over n minus 1. And now we can complete the square. If we add, we want n squared over 2n minus, divide by 2 square. So n squared over 4n minus 1 squared. And we're subtracting 1 over n minus 1 here. So this is the quantity we want to add to get us there. And if we combine these, we get n squared minus 4 times n minus 1 over 4 times n minus 1 squared. And this is n squared minus 4n plus 4. Oh hey, that's a perfect square. And factoring, we get n minus 2 squared over 4 times n minus 1 squared. So that's what we're going to add. And so we get n minus 1 times k squared minus n over n minus 1k plus n squared over 4 times n minus 1 squared. And then minus n minus 2 squared over 4n minus 1 squared. And this quantity will equal the 1 over n minus 1. And so now I'm going to bring this outside of the parentheses, and we get n minus 1 times k minus n over 2n minus 1 squared. And then bringing this out, we get minus n minus 2 squared over 4 times n minus 1. What? Oh, you can't see the bottom of that. Sorry about that. Here. So now we're asking, when is this a perfect square? I need to move over to the next page to continue. Let me know if you want to go back. N minus 1 k minus n over 2n minus 1 squared minus n minus 2 squared over 4 times n minus 1 to be a perfect square. I'm actually going to factor out... No, wait. So it seems like at the very least... Oh! We need n minus 1 must be a perfect square. Right? Is that right? No. If it is, though, we do get a difference of squares, which we can work with. Yeah, let me just factor out the n minus 1 again. So we get n minus 1 times k minus n over 2 times n minus 1 squared minus n minus 2 squared over 4 times n minus 1 squared. And now we have a difference of squares. Wait, but factoring that will just get us back to where we started, I think. That's not helpful. So I'm gonna let this equal r squared. We could, but that would be just putting in the form we had before. Like, it would be putting it, back into, this form. Which, I mean, we could. N minus 1 times k squared minus nk plus 1, right? Plus 1 equals r squared. So k times n minus 1k minus n equals r plus 1 r minus 1. What if we take this form and multiply both sides by n minus 1? Or better yet, 4n minus 1. Okay, there is something here. If we bring the n minus 2 squared to the other side, we get 4 times n minus 1 squared. K minus n over 2n minus 1 squared equals 4r squared n minus 1 plus n minus 2 squared. Now there's a problem here. One side is a multiple of n minus 1, the other is not. So these can't be equal. Because they're all supposed to be integers, right? So they can't be equal to each other. Which implies that this expression is never true for n and m greater than 2. Because this can't be a perfect square. Provided I did all the computation correctly. You may want to double check it yourself. It would also explain why you are having so much trouble if there's just no solution. How what? That's my hot take on it anyway. Um you probably want to double check my steps and make sure I didn't make like an arithmetic error along the way. You probably want to double check my arithmetic along the way, in case I made a silly error. But from what I see so far, it doesn't look like there can be a solution beyond 2.